In this case, in this picture, the handle shown in white has index 2. And then I attach a handle of lower index, which has, which in this picture has index 1. So let me call this H1 and this H2. The attaching sphere of H2 can be made by using a small isotope, can be made disjoint from the belt sphere of H1. Well, here the attaching sphere is just these 2 points. And the belt sphere is again 2 points. So we can transform this picture into this one. By using isotope.
Sorry, I don't quite understand how this head is a true handle.
This the hat is a 2 disc.
Yes.
So it's a handle of index 2.
Oh, okay.
And it's sort of difficult to draw the whole handle, so I just drew the core. And similarly, this is the core of the one handle. So attaching a 2 handle first and then a 1 handle is equivalent to attaching a 1 handle first and then a 2 handle.
And so the belt sphere does not lie in this plane or on this hat. It just is something.
It's very close to the hat, but not on the hat. Do I need to draw again the belt sphere and the attaching sphere?
Ну да.
Надо, хорошо. Так как
надо просто размер.
ну, да. Сейчас вот та часть, она уже не видна, да? Хорошо. Давайте здесь нарисуем. Okay, again, the picture we already saw. So the handle is the handle of index k.
Но ручка-то у тебя полая.
Нет, the handle of index k is dk cross dn minus k. So the core is dk cross 0. The attaching sphere is the boundary, and the belt sphere is the belt. The belt sphere is 0 cross Sn minus k minus 1. So, in particular, if we have two handles such that
Да, Леша, я все-таки не понимаю, ну, ручка, почему у тебя ручка это диск умножить на диск, а не диск на сферу?
Ну, по определению.
Ну, это многобордизме диск умножить на диск, а просто, если вы так многообразие определяешь, диск на сферу. Ну, ты вырезаешь диск из твоего многообразия и должен вклеить то, что границы имеет сфера.
Ну, значит, в нашей ситуации мы приклеиваем, значит, вот такого сорта ручки.
Ну, это как раз ваш кабардизм.
Ну, нет, не только ваш кабардизм. Мы pass through a critical point, we pass from one manifold with boundary to another manifold with boundary, and the procedure is we take this this thing which has the same dimension n. We take this part, which is in this picture 2 disks. We map this part to the boundary, and then we get another manifold with corners, which can be smooth. So it's basically a manifold with boundary. Does the picture make sense? Do you want me to check this in general?
How does this preserve this smooth structure? Because when you're starting from that had to be plane, maybe you lose the smoothness.
Sorry, say again?
When you use these orthogonality, maybe you lose your smooth structure. Is that obvious that we can save this smoothness?
Let's consider this in more detail. I take this this core. using isotope, I transform it into this core. It's sort of clear from the picture that if I take small disks about the boundary of the core, I can also isotope them to small disks about these 2 points, and the smooth structure is the same. Yes.
So can you see just some general transversality arguments?
Yes, basically the argument is already clear in this picture. Here we have So here we have 2 points. They have dimension 0. And here we have another 2 points. They also have dimension 0. And both couples of points live in a 2 manifold, which is the boundary of what we get after we attach the 2 handle. Well, in a 2 manifold, 0-dimensional submanifolds usually don't intersect.
But you said something about isotopic disks.
Yes, and then what we really attach is not just points but disks.
Yeah,
but
disks don't have the required codimension.
Well, yes, but they can be made arbitrarily close to the points. So basically, my claim is that this dimension count works in general in exactly the same way as it does in this particular example. Okay. I suggest we leave the rest of this proposition as an exercise, unless there are some parts of it which aren't clear. And as is also clear from this picture, the number of the critical points remains the same for every index. Okay, so we've proved the Morse inequalities, and there are several other proofs of the same inequalities, but in particular there is a more algebraic proof in the book Morse Theory by Milner, which I think is also very illuminating. Okay, I wanted to prove a couple of applications of Morse theory. For example, does everyone know how to prove the Lefschetz hyperplane sectional theorem? And question. Actually, before asking this question, does everyone know what the Lefschetz hyperplane theorem is all about? Okay, so it's a very useful theorem. Let's talk a little bit about this theorem. I don't think we need this. We'll need this picture next time, but probably not today. I hope not. So, It's a nice application of Morse theorem. So what does the theorem say? Well, let me start by saying complex analytic, although we'll see in a minute that in fact it's algebraic. So suppose we have a compact complex analytic manifold. Does this expression make any sense? Suppose L is an ample line bundle. Which is the same some power of it is very ample. Does this expression make any sense? Okay, let me briefly explain what this means. A holomorphic holomorphic line bundle is very ample if and only if by taking its global sections we get a projective embedding. Now, what on earth does this mean? Well, it simply means the following thing. We take a basis and we associate to an X the point S0 of X, S1 of X, etc., Sn of X. Now, what does this mean? Let's see. Where does S0 of X live? It lives in the fiber of L prime over X, and same goes for S1, etc. Now, of course, there are several ways to identify the fiber with C. But every time we choose a different way, all S0, S1, and so on get multiplied by some non-zero complex number. So, if at least one of these is not zero at x, then we get a well-defined element of CPM. And moreover, we require that this map should be an embedding. Does this make sense? Okay, so this is very ample, and an ample bundle is a model such that, well, it may not be very ample, but some power of it is. Okay, so the Lefschetz hyperplane section theorem has two versions. And actually, one of these follows from the other, but nevertheless, I'll state both. Version 1. Version 1 says, let's take a section, let's take the zero locus of the section and throw it away. Then the result is a CW complex. Is a homotype equivalent to a CW complex. Of real dimension less than or equal the complex dimension of M, and this is something which is quite well. It's sort of. Okay, so let's not get distracted. The real dimension is less than the complex dimension. Now, second theorem. Again, let's take a section. Let's take the zero locus and let's take the embedding. Now, my claim is that this, the embedding of the zero locus into M. My claim is that this embedding is very connected. How much connected? Well, let's see. The claim is that the relative homotopy groups are zero in degree less than or equal n, or is it strictly less? I think it's strictly less. So what it says is that low-dimensional homotopy and homology groups of the zero locus are the same for Z of S and for M. Which is which implies several other versions of the Lefschetz hyperplane theorem that you may have seen in an algebraic geometry course or a course in a related subject. There's just one thing. Just one thing we need to be careful about. Do we want to assume that Z of S is smooth? I think for the first one we don't need it. And what about the second one? Yeah, for the second one, I think we do need. Yes, so here we do need to assume. Here we need to assume that Z of S is smooth. Ну да, то есть на самом деле, значит, есть там какая-то ученая теория Морса имени Горевской Макферсона, там, которая работает там, ну, в общем, в каких-то более общих предположениях, но сейчас мы про это не будем. Okay. Well. Let's prove the first statement, and then we will see if we want to prove the second. Now, but before we prove anything, does this make sense? Okay. My first claim is the complement of Z of S in M is isomorphic to to a smooth affine subvariety of some complex vector space. Now, does this make any sense?
Well, it follows from the fact that we have an embedding.
Yes, we have an embedding for some power of for some power of L, but Z of S is exactly the same as Z of Sm for n greater than 0. If I take something, a section of L, then the mth tensor power of the section is a section of the mth tensor power. Now, this is a section of the mth tensor power, but I assume that the m is such that the mth tensor power gives an embedding. Let's look at this formula. It follows from this formula that each of the S0, S1, etc., Sn is the preimage of a section of the bundle O of 1 on CPN. So basically all sections, including this one, pullbacks of the sections of O of 1 on CPN. Well, so the zero locus of this one is the preimage of the zero locus of a section of O of 1. But what is it? It's a hyperplane. Now, what do I get if I take the image of M under an embedding and throw away the intersection with the hyperplane? Well, I get a smooth subvariety of CPN minus a hyperplane. What is it? It's Cn. Okay. Let me call this subvariety M. Let's construct a Morse function on N such that all critical points have index less than or equal n. Well, I take some Hermitian scalar product on Cn. Does everyone know what a Hermitian scalar product is? Well, now I take this function fx. I fix an x, and I take the function fx of y is this, the distance squared, which is x minus y, x minus y. Hold on. What's this? Okay. Okay. Let's see. So the first claim, which I do not want to prove, is that for almost every x in Cn, the restriction of fx to n is Morse, and all critical values are distinct. This is proved in Milner's book, and it's basically yet another application of Sard's lemma. Now, now I want to prove. I want to use this function, and I want to prove that all critical points have index that does not exceed n. By the way, functions which have these properties are called strictly Morse, or strict Morse.
give like conditions in terms of curvature for a point to be bad.
Yes.
But I don't think that we insert lemma to tell anything.
To prove that almost all x for almost all x we have something, we usually need Sard's lemma.
I mean, it basically follows from the fact that this submanifold is not all Cn. And then for some distinct points which are determined by points on this manifold,
one needs to be careful. So, so a point is bad if and only if x is bad if and only if it's a focal point of some element of some element of n. Well, for every element of n, there are finitely, and for every normal line through this element, there are at most finitely many focal points. But then we need to count all focal points for all normals and all elements of n.
Okay. But then it's like standard argument of the back measure that we don't. That if it was a set of measure 0 and then we take like countable many of them, we don't get all this space.
Which is Sard's lemma.
Okay, maybe I don't know Sard's lemma.
Well, it's exactly the same argument which is used in the proof of Sard's lemma. By the way, one needs to be careful with maps of finite smoothness when applying Sard's lemma. Here we assume that everything is infinitely smooth, but for finite smoothness there's there are some surprises which I don't want to go into at the moment. Okay. Okay, so let's choose one x such that and set f equal fx. Now we want to prove we want to prove this, and let's take a critical point. Then what? And let's assume that x is not in n, which we are allowed to do. Now I want to put After applying an isometry, we may assume that I want the critical point to be I want this point P to be the origin, and which I can always assume. Then I want to decompose Cn as C small n plus Cn minus n, and I want to represent. There are no, it's an S. There are two capital N's, which is these two N's are completely unrelated. Let's I don't know. Let's call this X. Sorry about that. Okay, I want to represent X as the graph of a function. Let's also okay. I have 2 minutes left, so I'll just state the rest of the proof as a series of problems. Let me call this this element x naught to make it clear that this is not the same as this x. So we can take x naught inside 0 plus c n minus n. Now, P critical implies implies that 0 is a critical point of G. In other words, G is a holomorphic G is a holomorphic function defined in the neighborhood of the origin in Cn. Okay, my claim is since the origin is critical, the origin is critical for G. Now, the quadratic part quadratic part of f at the origin is x goes to the modulus of x squared plus the real part of q of x, where q is a quadratic form. A complex quadratic form. And this is just a straightforward calculation. Now, if I have a complex quadratic form, maybe degenerate, and take this expression, my claim is the index of this real quadratic form will always be less than or equal n. And this is just linear algebra. Why? Well, every quadratic form over C is a sum of squares. This thing is so this thing is the same as the sum of ax modulo squared plus the real part of a sum of squares. But this quadratic form definitely has an n-dimensional subspace, the real n-dimensional subspace, on which it is a positive definite. So the index cannot be greater than n. There's a different proof in Milner's book.
Не анимается. Если честно.
Okay, so the end was a bit sketchy, but we have to. I think we have to vacate the room. We have to vacate the room soon. Now, the second part is actually similar. Except that we consider a Morse function on which is 0 on z of s, and which is equal 1 over f on the affine part. And then we smooth it a little if there are problems at infinity. And then if f only has critical points of index at most n, 1 over f will have critical points of index n or greater. So m is obtained from z of s by attaching cells of index at least n, and that's where we get this statement about the homotopy groups. Okay, let's leave this last part as an exercise, but we'll talk about it later if there are people who want to talk about it later. Are there any questions, comments, etc.? Okay, so I did receive an email from Grisha who says that this seminar clashes with Lando Kazarian. Well, is there anything we can do about it?
Maybe start one.
Yes, but Vladimir has 2 lectures before this one, which is and those 2 lectures aren't movable.
Ну, вроде да, может быть, еще можно начать. Я спрашиваю.
Ну, в общем, смотри, значит, как тебе удобнее. Okay, well, then this is it, and I think we.
Как я понимаю, есть другой способ доказывать неравенство Морса, но который как раз у Милнера.
Сейчас, как это выключать? Как шутку выключить? Так, и чего? Пауэр, правильно?
Да, я на кнопочку долго нажал.